Hi everyone. So I'm Rhydian. I'm one of Rhydian's PhD students, and so my work focused on looking at simulation and machine learning for fusion energy application. That was meant to be my blurb, but got lost in translation. But so today, me and Ben are going to give a joint talk. So I'm going to present a platform we've developed at Swansea, and then Ben's going to sort of show how it's been used in an image-based simulation context. I'll start off with the motivation of the platform. So I'm sure many of us have probably been at a conference at one time or other, and you've seen a talk you've enjoyed, and you've asked someone, how can you go and use that bit of work? And they replied with something along the lines of, well, you need countless different software packages, some of which might be commercial. You also need certain operating systems. And on top of that, they're the only people that really know how to get it all to work together. We wanted to kind of overcome this thing and make a package that made it very easy for workflows to be passed between different people. So our first goal was automation of the workflow. So most engineering workflows will have sort of your CAD and meshing, simulation, and then visualization software packages. And then, as most of you in this room are in the imaging side of things, there's a lot of other software packages as well you need to use. And it's quite often that there'll be manual steps in between those, using each of those softwares. So it can become quite difficult then for other people to use the work you've done because of a lot of knowledge that maybe you know and other people wouldn't. Second goal was portability. So we wanted to make it very easy for people to be able to use VirtualLab on any sort of computer system, whether it's a personal computer or a supercomputer. I'm sure when we've all tried to install a software package at some point or another, we've seen errors like this that probably leave us looking a lot like this. I mean, I've spent probably the first year of my PhD looking like this. So the third goal then is contribution. So we wanted to make it easy for others to add their own work to package and so it can grow quite organically. And then the fourth one is sort of probably more prevalent to me was rapid data collection. So this was looking at ways that we can produce large quantities of synthetic data that we could use to train machine learning models. So there's sort of three ways that we can do this. So the first is parameterization. So that is that any important parameters to the workflow are in a sort of conveniently located file and are easy to change. And what this means is you can set up a lot of different analyses prior to any project. And then, so if you have a suitable parallelization tool, you can sort of run a lot of different jobs together at the same time. And then if you can make it compatible with a HPC system, then you're flying, and you can make hundreds, if not thousands, of different data points in a very short space of time. To give you a quick bit of code overview, so some of you may know about containers and some of you may not, so I'll give you a brief overview, but they're effectively a bit like a shipping container. From the outside, they all look the same. On the inside, they're all different. So the idea is that they can be used on sort of any operating system, and then inside, there's an operating system itself, and there's all the dependencies that your package or app or software will need. So this makes them quite powerful, and sort of removes the need for having dependencies on your system, which usually always leads to things breaking. One thing is they're immutable. So once you made a container, you can't really change it, but you can sort of bind things from your host system into the container to make it a little bit easier. So using VirtualLab, so you may think of this blue square as your computer, your host system. So if you wanted to use it, you only need three different requirements. So one is Aptainer, so that's a standard sort of containerization tool. Git, and then Python. And the Python we'd use on the host system is very minimal, so you can work on almost anything with Python 3 and above. So then, if you want to install it, the only difference you see on your system is one folder, basically, that actually should have all the scripts in it. Nothing else would be added to your system at this point. All the sort of Python dependencies, NumPy, SciPy, all those kind of things would be put in a container called the manager container. So this would contain things like PyTorch and machine learning algorithm libraries. And effectively, that means that it's sort of a bit like an Anaconda system, where it's kind of isolated from the system, but it's just an easier way of doing it. And obviously, so you can run through a script and everything works fine, but at some point you will need to call external software. So to do that, we have a server running on the host system in the background, and at some point the manager container will send a job to the server and say, I want to run piece of analysis using an FEA package called Aster, or there's Paraview. Quite a lot of different packages we've added over time. So all of these packages are in their own individual containers, so you can download any ones you want, and it effectively means that you should work out of the box on any sort of system because they're all in containers. So the structure of VirtualLab is the sort of 3 different tiers to it, as it were. So you have an experiment. So this is a top tier. So you have things like a tensile test or laser flash analysis. So what I used for my PhD was Hive, which was a fusion relevant experiment. Within each experiment, then they'll use different methods. So meshing, simulation, data analysis, machine learning, optimization, things like that. And Ben will give a bit more an overview of some of them afterwards. And within each of those, you sort of use different modules. So these are the bits of software we put in containers to make our life easier. For example, the tensile test would look something like this. You have meshing software, a meshing method which would use the Salome preprocessor. Sim will use the Codas FE solver, and then data analysis will use Paraviz for visualization or whatever we need to do. So we did want to give a brief demo, but maybe more trouble than it's worth. So this is just on the left. You have what is the run file. So this is what kind of what you kind of use to launch analysis. So you have a few definitions on the top, and then as you go down, you have your meshing, your simulation, and your GA data analysis at the bottom. And then you can see where it says parameters, masters, training parameters. So this is the file on the right. So this basically has all the important bits of information you need to run your analysis. So things like assigned to the mesh, there are geometric parameters and meshing parameters, and then the simulation are things like forces and displacements and so on. We also spend quite a lot of time doing quite a lot of documentation for it. It's not my favourite task, but it's there. So finally, I'll give you a brief overview of what sort of I've used it for during my PhD. So Hive is a reasonably small-scale fusion experimental facility. So it's by induction to verify extremes, and effectively it's used to thermally load the top surfaces of plasma-facing components that we're using fusion devices. So it uses a induction heating coil to heat the surface while it has coolant running through the pipe to actively cool the component. Unfortunately, there are sort of a few limitations to the experimental facility. So one of them is setup uncertainty. So induction coils are very, very dependent on how their proximity to the components. So very, very slight changes can have quite a big impact on the results. So if you move the coil 1 millimeter, you have 110 different degrees difference in the maximum temperature, which 1 millimeter is going to be very, very hard for you to actually measure, whereas it's going to have a big impact on your results. And the other one is the sort of limited diagnostics they have available. So they have an infrared camera, but it is blocked by the induction coil, so you can't really see the surface that you want to see. And then you have thermocouples, which will give you point temperature measurements on the surface, but the problem with that is that A, you can't put them on the top surface where you'd kind of want to know where the temperature is, and B, they're prone to failure and they take a long time to fit and so on. So the outline of my PhD was improve this with machine learning. It's quite vague. So it's a brief idea of sort of Hive. The facility uses mesh again with Salome. In this example, it uses SIM, but it uses Codas and Hermes, which is a electromagnetic finite element solver. And so in this example, I made 400 different simulation points. Then with an ML method, I made about 10 different machine learning models, and then sort of use them to plot different bits of results using the data analysis method. And so this is what we sort of end up with. So on the top line, we have temperature profile throughout the 3D components. So the first one is the finite element results from Codas and Hermes. The middle one is a surrogate model, and on the right then is the difference. So at the top is temperature, bottom is the von Mises stress state. So to make these, I used Gaussian process regression with principal component analysis to reduce the dimensionality of the problem. And then basically, with using these, then we could sort of help solve quite a few different things that were problems for Hive. So one of these was solving inverse problems. So their approach, whenever they have something to test, they'll always sort of say, oh, I'd like this to get to 700 degrees. Their approach was to put it in, do an experiment, check the temperature, and then tweak some knobs until you got to the temperature you wanted, which is pretty inefficient, especially when you have to wait for chambers to decompress and so on. So with using the surrogate models as part of a least squares optimization algorithm, we could identify sort of 8 different experimental parameters, and basically, if you throw them back into a simulation at the very least, you'll see a 0.5 degree out in terms of the maximum temperature you'd expect. So that, quite happy with that. But then we can go further as well. Because we have a surrogate model of our stress state as well, we can look at things like, well, say I wanted to get to 700 degrees, but I also wanted to minimize the amount of stress in my component. Well, you can do that, and basically, in this example, we get to 69 degrees, 69 megapascal in the maximum stress of the component. And then similarly, you can see what the maximum stress is, and it's 150 megapascal. And then the other sort of way I was able to use these surrogates was to predict the full field temperature. So as I said, from your thermocouples, you might have 5 or 6 different point temperature measurements on the surface, which don't really tell you an awful lot about how suitable the component is for fusion application. Whereas with using the surrogates, we'll be able to predict what the full field temperature is throughout the component. And once you have that, you can tell what the full field, what the stress state is throughout the component as well. So it sort of allows us to enrich the data quite a lot. So we can now say, from these 6 temperature fields, how much stress is the component actually under, which so helps characterize the benefits of any component. So yeah, thank you. And with that, I'll hand you over to Ben.